Alright, so as we continue in Chapter 9, we move into writing Lewis structures. Now, when we talk about Lewis symbols, like we did last time, we talked about how a single atom has a certain number of electrons around it, and those electrons are all indicated by dots. When we take two atoms and we bond them together, we change those dots into a line, so one pair of dots becomes a line to get a single bond. Now we're going to do that, but not for more than two atoms. So we did it for fluorine, and we did it for water. Now we're going to do it for atoms that are much larger and more complicated. We won't get too crazy, but we will do it for larger molecules. Okay? As with lots of things in chemistry, we have a few rules, and so let's go over the rules for drawing these Lewis structures. The first is that we're going to draw a skeletal structure. And so that just means we're gonna put the atoms in the place that makes sense, and we're gonna go ahead and draw a bond between them. We know that atoms are connected by bonds. We can skip the pair of electrons between them. Go ahead and draw a bond. We know that one bond represents two electrons. For these rules, we're going to put the least electronegative element in the center. Right? There is an exception to that. That exception is hydrogen. If you remember from our last video, hydrogen only likes to make one bond. He only wants two electrons. He has, remember we called it a complete duet of electrons. And so, because he can't bond to more than one thing, he'll never go in the middle of our molecule. Once we have our basic outline, our basic structure, then we're going to start adding in some electrons, but we need to know how many. And so we count up the number of valence electrons for all the atoms. If we have a charge on the molecule, let's say it's a polyatomic ion, for example, we're going to add one for each negative charge and subtract one for each positive charge. So, for example, NO3, if we were going to draw NO3 minus, nitrate, nitrogen has 5 electrons, oxygen has 6, and there are 3 of them, and this means that there's 1 extra electron, and so we'd be dealing with a total of 24 electrons for NO3. Okay? Once we have the right number of electrons, and we're sure that that's how many we should be dealing with, we need to make sure that that molecule has no more, no less, but exactly that number of electrons. We're going to complete the octet for all those atoms, and we're going to start the atoms on the outside. We call those the peripheral atoms. We're going to start by adding electrons, lone pairs of electrons, to those atoms on the outside of the molecule, and save that central atom for last. Because if we don't have enough electrons, it's likely that we'll have to make a double or even a triple bond, and almost always those extra bonds go from the peripheral, those outer atoms, into the central atom. Okay? Let's do several examples here in a row to get us started. Draw the Lewis structure for nitrogen trifluoride, in which all 3 fluorine atoms are bonded to the nitrogen atom. And so this particular question gives us a little hint. It says all 3 are bonded to nitrogen. Fluorine is the most electronegative. Nitrogen is the least electronegative. And so I'm going to start this way. For right now, until we get into Chapter 10, sort of how you arrange the atoms around the central atom doesn't really matter. When we get into Chapter 10, we're going to talk about molecular geometry, and once we do those geometries, then how we draw it actually matters a little bit. Okay? In NF3, nitrogen has 5 valence electrons. Fluorine, each one has 7, and there's 3 of them. So that's 21 and 5. So we should have a total of 26 valence electrons. Okay? So in my molecule, I'm going to start adding electrons to each of the outer atoms first. Those are the fluorines, before I start adding electrons to the inner atom. So I'm going to start with this fluorine here. Notice that he already has one bond, and so that's already 2 electrons. Right? So he's got 2, he needs a total of 8, so I need to add 6 electrons to this fluorine. I'm going to do that in 3 pairs of electrons. Remember, we keep electrons in lone pairs as much as we can. So fluorine is going to have 3 lone pairs of electrons. And that's a total of 8 so far. So we start with 26, we've used 8. Here's 2 in this fluorine at the bottom. We're going to give him 3 lone pairs as well. There's 8 more, that's a total of 16. The fluorine on the left, give him 3 lone pairs. That gives him 8 electrons as well. And so that's a total of 24 electrons. We've still got 2 electrons left over. And this nitrogen only has 6 around it, right? He's got 2 electrons in each bond. And he still needs a lone pair. So we're going to give him a lone pair at the top. And he is happy. And so this is the correct Lewis structure for nitrogen trifluoride, NF3. Okay. Moving on, nitric acid, HNO3. Tells us that the 3 oxygen atoms are all bonded to 1 nitrogen atom, and that this hydrogen atom, the one that comes off for the acid, is bonded to 1 of the oxygen atoms. So, nitrogen in the middle again. We're going to put those 3 oxygens around the nitrogen, and it tells us that that the hydrogen is on 1 of those. It doesn't tell us which one. It doesn't really matter which one. And so we're going to go ahead and pop him in there. Okay. And so how many electrons do we have? Well, nitrogen has 5. Oxygen has 6, and there are 3 of those. So that's 18. And hydrogen, he brings 1 to the table. So that's a total of 24 electrons. Hydrogen only needs 2 electrons. He's got 2 electrons in this bond, and so we're not going to add anything around hydrogen. But now we're going to move into the oxygens. The oxygens all need 8, and so I'm going to count a little differently this time around. We need 24 total. We've got 2, 4, 6, 8 in bonds already. Right? We've got 4 bonds, 2 electrons each. So we've already got 8 electrons counted for in bonds. That means we have 16 left. And so I'm just going to count up and see how far I get. So I need 16. 1, 2, 3, 4. That oxygen has 8 around him now. 5, 6, 7, 8, 9, 10. The oxygen on the bottom has 8 around him now. 11, 12, 13, 14, 15, 16. That oxygen has 8 around him. So we've drawn in 24 electrons, again, 8 around this oxygen, 8 on the oxygen on the left, 8 around the oxygen on the bottom, and a total of 8 around the oxygen on the right. So that's a total of 24 electrons that we've already used. The problem is that this nitrogen only has 6 electrons. Nitrogen really wants to have 8 electrons, if at all possible. And so what's going to happen is we're going to use a lone pair of electrons from one of the oxygen atoms, and we're going to turn it into a shared pair of electrons. So instead of being only with oxygen, it'll now count toward the octet of both oxygen and nitrogen. We'll talk in a minute about formal charge. Formal charge helps us determine which oxygen atom we take it from. But because this oxygen on the left already has 2 bonds, oxygen really does not want to make more than 2 bonds. And so we're going to pull a lone pair. I'm going to do it from this oxygen here. I'm going to pull that lone pair in to form a double bond. I'm going to redraw this structure. So now I have an oxygen that's double bonded to this nitrogen with an oxygen at the bottom, an oxygen on the right with his hydrogen. I'm going to go ahead and redraw all of those lone pairs of electrons as well. Okay. And now you can see that the oxygen on the left has 8 electrons, 2 sets of lone pairs, that's 4, plus 2 bonds, a double bond. And so that's another 4. And so that oxygen has 8, nitrogen has 4 bonds, each bond is 2 electrons, nitrogen has 8 as well. And so now this satisfies the octet rule for all the atoms except hydrogen. He only wants 2 anyway. And we've used the right number of electrons. I could have just as easily gone from the bottom oxygen to make that double bond, and it would have been A-OK as well. I don't want to take it from the oxygen on the right. Since he already has 2 bonds, he doesn't really want to make more than that. I'll talk more about that when we get to formal charges. Alright, so now we have an ion. This is the first ion that we've dealt with, CO3. Between these two, carbon and oxygen, which is the least electronegative? Turns out that it's carbon. Carbon goes in the middle. We're going to put oxygens around him. Okay. Carbon has 4 electrons. Oxygen is 6, but we've got 3 of them. So that's 18 electrons. And then because of this 2 minus charge, we've got an additional 2 electrons. So that comes up with 24 electrons. Okay. 24 total electrons we need to arrange around this carbon. We've already used 6 in bonds. And so here we go. Here's 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There are our 24 electrons. We run into the same situation that we had with nitric acid. We've used all of our electrons, but the carbon, that central atom, doesn't have a full octet. What are we going to do? Well, we're going to have to do the same thing. Take a pair of electrons from one of the peripheral atoms, one of those oxygens, push it in to form a double bond. Now, all of these oxygens look exactly the same, so it really doesn't matter which one you take it from. And so I'm just going to take this pair of electrons, I'm going to move it in, and so we end up with carbon that's double bonded to an oxygen on the right, bonded to an oxygen on the top and to the left. I'm going to redraw in those lone pairs of electrons, being sure that I don't draw an extra set around that oxygen on the right. Okay. We need to do one more step since this is an ion. If we looked at this Lewis structure, we'd have to do a good amount of sort of counting and calculating to figure out that this was CO3 2- and not just CO3. To save us a little bit of trouble, whenever we have an ion, we put it in big brackets and put the charge of that ion out to the side. Okay? And so whenever you see a Lewis structure, whenever you draw a Lewis structure for an ion, always put some brackets around it and put the charge up in the corner. Okay? Okay. So I mentioned we'd talk a little bit about formal charge. Here we go. Here's an example where we have 2 different options for how to draw that skeletal structure for a molecule called formaldehyde, CH2O. We could either draw them all in a line, as we see on the left, or we could draw it in sort of this Y shape, as we see on the right. Formaldehyde should have a total of 12 electrons, okay? 4 from the carbon, 2 from the hydrogens, and 6 from oxygen. So a total of 12 electrons. In each structure here, we have drawn 6 already. And so we end up with drawing 4 more on the oxygen, and we only have 6 left. We only have 12 total, so we only get to draw 2 on the carbon. Why did I draw on the oxygen first? Oxygen's more electronegative, and so he gets the lone pairs before carbon does. Okay. Carbon does not have a complete octet, so I'm going to erase this pair of this pair of electrons. I'm going to draw in a double bond there. Right? One option. In the other drawing, we've got 6 electrons, 7, 8, 9, 10, 11, 12. That's all of our electrons. Carbon still doesn't have an octet. So again, I'm going to take one of these pairs and I'm going to make it a double bond. Okay. How do we know which of these two structures is more legitimate? Which of these two structures is correct? Well, we use something called formal charge. Okay, formal charge is not a true charge, like an electron charge, but it's a way that we sort of keep track about which Lewis structure is a better Lewis structure. Okay? And so our formula for formal charge, I'm going to make that Fc for formal charge, is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonds. Okay. Formal charge is something that each atom has, not as the molecule overall, but every atom will have a formal charge. The goal is that we reduce formal charge as much as possible. I'll write that down here. So the goal is to reduce formal charge as much as possible. Right? That is, we want to get it to 0. We don't want negative formal charge, we just want 0 formal charge. So if we look at this hydrogen on the left-hand side of the left-hand molecule here, I'm going to do these formal charges up here. So for the first hydrogen, right, the number of valence electrons in hydrogen is 1. The number of non-bonding electrons for that hydrogen is 0. And the number of bonds that that hydrogen has is 1. 1 minus 0 minus 1 is 0. And so this hydrogen has a 0 formal charge. This hydrogen is exactly the same. He's also going to have a 0 formal charge. So the carbon starts with 4 valence electrons. It's got 2 non-bonding electrons. And it's got a total of 3 bonds, right? That double bond counts as 2 bonds. And so 4 minus 2 minus 3, that's negative 1. The oxygen here starts with 6. That oxygen has 2 non-bonding electrons and also has 3 bonds. So he's positive 1. Okay. Now let's take a look at the one on the right. The hydrogens again are identical. They both start with 1 valence electron. They have no non-bonding electrons. And they have 1 bond, so that's 0. So both of these hydrogens have a formal charge of 0. The carbon starts with 4 electrons, has no non-bonding electrons, and has 4 bonds total. That's 0. And oxygen starts with 6. In this Lewis structure, he has 4 non-bonding electrons and has 2 bonds. He comes out to 0. And so as you can tell, the formal charges on the right-hand molecule are all 0. And so that is a better Lewis structure. Okay? Generally speaking, the sum of the formal charges for the atoms in a molecule have to equal the charge on the molecular ion. In this case, they both do that, right? They both have formal charges equal to 0 overall. However, we've reduced the formal charges to 0 on every atom for the molecule on the right. Okay? So, formal charges for the carbonate ion. Well, we've done carbonate already. We know that carbonate is a carbon like this. We did this a few slides ago with a 2- charge, right? That is our Lewis structure for carbonate. Let's calculate the formal charge for carbon starts with 4, no lone pairs, 4 bonds, that's 0. 0. How about this double bonded oxygen? I'm going to indicate that he's double bonded by giving him that double there. Starts with 6. He's got a total of 4 non-bonding electrons and 2 bonds. He's 0. And those single bond, 0, I'm going to write that in. That single bond oxygen starts with 6. They've both got 6 non-bonding electrons, but they also each have 1 bond. So that's -1. We can't get all of our atoms to have a formal charge of 0 here because overall our ion has a charge. And so some of our atoms have to have a charge. And so having a -1 on that oxygen at the top and a -1 on that oxygen on the left give us 2 negative charges overall. 2 negative charges overall matches our overall charge on the ion. And so the structure that we drew, the Lewis structure that we drew, was in fact a good Lewis structure. Okay? This is the best Lewis structure for carbonate. So some things to think about when you do formal charges and as you're calculating those. As long as we have a neutral molecule, the Lewis structure where there are no formal charges, that's all 0, is preferable to one where you do have formal charges, non-zero formal charges. Right? Again, that's for a neutral molecule. Generally speaking, the larger the formal charge, the less likely that Lewis structure is to be very good. Right? That's point 2. And then for the last one, if we have to have a charge, in other words, if we have to have a formal charge in our Lewis structure, the most likely scenario is one where a negative formal charge is on a more electronegative atom and a positive formal charge is on a less electronegative atom. Right? And so negative formal charge goes on more electronegative atoms. Right? And that should just make sense. If we're going to have a negative charge, the atom that's electronegative is going to want to do that. All right. That's going to end it here. The next video we'll talk about resonance structures, or maybe more than one Lewis structure checks all of the boxes, as well as talking about exceptions to that octet rule, which atoms are okay having more or less electrons than 8. Okay? Take care.